So good morning, everybody. So I am Gaëlle Guyot from France. I am the Deputy Head of Research Team dealing with building performance at Cerema. Cerema is the French public agency for ecological and energy transition. And so today, my keynote is about what we know about smart ventilation. So my presentation is divided in three parts. First, the context, then what we know, the definition, the terminology, the strategy, the performances, and finally, what we need from researchers, from industrial, and from policymakers. So the context is that the building sector is facing multiple challenges due to the need to generalize a sober approach and to reduce the energy consumption, the CO2 emissions, the carbon footprint, the environmental footprint, and to increase the indoor air quality and health provided to occupants in buildings, and to increase the resilience of buildings, the resilience to climate changes, like the increase of heat waves and the increase of their intensities, and the resilience to environmental changes, like the increase of pandemics. So in this context, we can really say that ventilation, building ventilation, is at the heart of all these challenges, and that smart ventilation could be considered like a part of the solution. So my presentation today is based on the research which has been performed over the 8 past years in my research group, and it includes the recent knowledge that we collected during the Annex 86, which is the Energy Efficient Indoor Air Quality Management in Residential Buildings Annex. And in this annex, there is a subtask dedicated to smart ventilation, the ST4. I am the leader of the ST4 with my co-leader Jakub Kolarik from DTU. And we are trying to push an international effort about the promotion of smart ventilation strategies in residential buildings. So, what we know. A definition has been given by the AIVC in 2018. So this is a short version of this definition. This is a process to continually adjust the ventilation system in time and optionally by location in order to provide the desired indoor quality benefits while minimizing energy consumption, utility bills, and other non-EAQ costs such as thermal discomfort or noise. So with this definition, you can understand and we can consider that demand control ventilation is a specific subset of smart ventilation. So smart ventilation includes a wide range of systems currently available either in the literature or on the market, depending on the type of sensing parameters, indoor parameters like humidity, occupancy, pollutants concentration, or outdoor parameters like climate, pollution, temperature, and so on. Depending on the type of sensing combination, the type of air terminal devices, depending the type of installations, centralized ventilation, decentralized ventilation, the type of techniques, balanced ventilation, exhaust only, supply only ventilation, or hybrid ventilation, and the types of controls and control algorithms associated to the controls. So this is really a wide range of systems. Some words about the history. So while the term smart ventilation were first used very recently by the LBNL researchers, so Ian Walker groups, and have been increasingly used since, this concept of smart ventilation is not a new concept. Indeed, demand control ventilation emerged after the oil crisis of the early 80s with some European papers at this time. And so we can observe that more recently, a favorable context for smart ventilation exists, at least in Europe, pushed by the EPBD, so the Energy Performance Building Directive in Europe. And so today we have around 20, 30 demand control ventilation systems available on the market in some countries like such as Belgium, France, and the Netherlands. So a question is, what are the performances of residential smart ventilation? To answer to this question, we published a first state of the art in 2018. And at this time, we observed that most of the systems, they were based on CO2 or humidity. And we had some systems with combined CO2 and TVOC sensors or occupancy sensors and outdoor temperature control ventilation. And in this first state of the art, we observe energy savings up to 60%, so the part due to ventilation. So such savings could be obtained without compromising and sometimes even improving the indoor air quality. And so in this first state of the art, we had 38 studies published between 1979 and 2016. And so we clearly highlighted at this time a clear potential for improving the indoor air quality and at the same time saving energy. So today, in 2023, we are updating this first state of the art. So in the framework of the Annex 86, two researchers, Daniela Mortari from PUC-PR in Brazil University, and she's hosted at this time at Cerema and Université Savoie-Mont-Blanc, and Dr. Yu Wong from Blantz, New Zealand. They are doing a huge work analyzing the published literature. And it will be published in the new AIVC technical note soon. So at the first stage of their work, they identified nearly 800 reports, and after screening all these data, they are now analyzing around 60 reports dealing with smart residential ventilation. So they clearly highlighted that we can say that there is an increase of publication on that topic since 2018 in the conferences and in the journals. They propose a rank of institutions according to the number of articles. So in the top 5, we have Ghent University, Lawrence Berkeley, National Laboratory, Renson, and the DTU and Cerema, and the Ohio State University, sorry. So they propose as well both viewer results, which is quite interesting. So here I present the keywords occurrence by year. So in 2019, it was in blue, and it moved to yellow in 2022. And so we can observe that we moved from the keywords ASHRAE standard, energy utilization, smart buildings, to other keywords like automatic control, algorithm optimization, and health. So it was what we know, and now we move to what we need. So clearly, I highlighted 5 needs for smart ventilation. The first one is about the need of sober systems adapt to the challenge of our decade. So you may know that on 9 planet boundaries identified by the Stockholm Resilience Observatory, 6 of the planet boundaries have been crossed in 2023. So at this time of the history, we really need ventilation systems which are sober, so which are using less very low amount of energy and low amount of resources, that are reliable and that offer long-term performances over the ventilation system lifetime, which has been estimated around 20 years. And the good news is that many of them already exist. Secondly, we need robust and improved performance-based assessment schemes because it remains a barrier in many countries. And this is not a new topic, these performance-based assessment schemes, because already in the 80s, the final report of the Annex 9 described the two approaches which could be used for ventilation standard. So the first approach is the prescriptive approach, in which we fix an outdoor airflow rate, and the air quality approach that we call today the performance-based approach. So with this approach, we fix a maximum pollutant concentration, for instance, and the ventilation airflow must secure the fact that the concentration stay below this threshold. So this is an illustration for these two approaches. So with the prescriptive approach, you will order to a taximan, turn left at the next traffic light, then take the first street to the right, go right ahead at the first roundabout, and so on. You will never do that. But if you use the performance-based approach, you will just say to the taximan, please, to the airport. So to date, however, most national regulations and standards, they are still using the prescriptive approach for ventilation, except in the field of smart ventilation. So we published a VIP paper some years ago on presenting that point. And why? This is because smart ventilation must undergo procedures or calculation in order to demonstrate their performances before being authorized or used in buildings in general. So here you can see an example of performance indicators, so energy and EAQ-based indicators, which allow to compare different systems. In yellow, this is a classic constant air ventilation, and the blue and green ones are more smart ventilation system. And you can compare here the performance depending 5 EAQ indicators based on CO2, PM2.5, formaldehyde, and humidity, and one energy-based indicator. We are trying to improve such schemes in the Annex 86, notably, and here this is a comparison of health-based indicators depending the smart ventilation strategies. So it's used the DALI, and you will hear more about this issue in another keynote of this conference proposed by Ben Jones. So when we work with performance-based assessment schemes, this is really important to include uncertainty and sensitivity of the results. You cannot just compare the system based on one point. So here you can observe the uncertainty of the different indicators depending the uncertainty you have on the input data. And so here we compare 5 ventilation strategies, some of constant airflow, some other are more intelligent, and you can see how for some indicators the results can vary. If you look deeper in the analysis and you look to the sensitivity of each of the output indicators depending the input variables, you can identify that, for instance, the emission rates, the velocity deposition for particles are very sensitive input variables, which will impact a lot the output indicators. So here I propose to stop before moving to the 3 last needs, because I really need to say that smart ventilation needs a special attention. Why? Because we know that ventilation in general suffers from a lack of quality of the design of the installation and of the maintenance. And as a result, for instance, in France, we have 50% of the buildings which don't comply with the regulation, which is quite high. And this is not only in France. And with the problem with smart ventilation is that we generally allow lower airflow at some times when or where we need low airflow. So, for instance, where there is no occupancy or low emissions and so on. So we have to secure even more the performances in order to make sure that the system doesn't stay blocked at this low airflow. And we have to secure this performance again over the ventilation lifetime, so around 20 years. So for that, we need requirements for sensors and actuators accuracy or longevity. We need to secure the long-term performance, and we need to adapt the inspection protocols for ventilation. So we only found one example. It is in Belgium regarding the requirement on sensors used in smart ventilation strategies. So in Belgium, the concept is that if you use smart ventilation, you can have a credit in an energy performance calculation for buildings. And if you want to have this credit, you have to comply with a requirement on the sensors used in the smart ventilation strategy. So here, these are CO2 sensors and humidity sensors. So first we need more studies about the long-term durability of the performances, because again, the ventilation lifetime is 20 years. So when we talk about long-term durability, it includes the intrinsic technological durability of all the components of the ventilation systems. So it can be tested in laboratory conditions, for instance, with aging studies. And secondly, it includes the robustness in use. So the robustness of all these components to the use made of them by the occupants. So the maintenance or the absence of maintenance, the cleaning. And so this is linked to different reasons specific to the occupant, like their understanding of the issues of the system and the way the system take into account their needs and their expectations. So on that topic, there is a lack in the literature. We found only 3 studies in 2023 when we reviewed the literature. We had nearly 0 input in the Annex 86 group at this stage. And when we say long-term, sometimes in the literature, it is only few months or 1 year, and here we need for a longer period. So here, this is an example of a study we are conducting in France, and we published the results in Energy in Building about the assessment of components performance in laboratory conditions. And these components, they were used after 13 years of operation in French residential buildings. So last but not least, the 5th need is to adapt the inspection protocols for ventilation and to require regularly inspection. So indeed, we observe emerging inspection protocols and quality management schemes for ventilation, and they should really include some specificities due to smart ventilation. We think that we should include a frequency of inspections which should be adapted to the long-term performances offered by the systems or the sensors. So not only at building commissioning. And the good news is that with some smart ventilation systems, they can offer online and continuing commissioning. So this is really a huge opportunity for securing the performance. So What we need to resume, we need sober system adapted to the challenge of our decade. We need robust and improved performance-based assessment schemes. We need requirements on sensors accuracy. We need more studies about long-term durability of performances. And we need adapted inspection protocols regularly required. And these are challenges for industrials and researchers and policymakers. They will pull and push the market of smart ventilation. Thank you for your attention.